Okay, so
I guess I'm going to do it, yeah.
You're the guy? Okay.
No one else wants to.
We'll try to go easy. Start booming.
You can go easy, you can go hard. I won't have much to be able to say.
Reaching for the fruit baker on the table.
That's right. All right, so this is the same thing as we had this morning, the DGVM carbon cycle. And we pretty much have the same kind of format. We tried to sort of answer the questions. Hope we get a good grade. So basically we started off with what exists now, and the way we sort of looked at it is what is likely to be part of what we sort of calling a core version of the next Earth system model, or at least in terms of DGVM and carbon cycle for the AR5. And basically the sort of motivation is taken together these components will close the carbon cycle, where we put close in quotes because it probably will not be a completely closed cycle, but be much closer to a closed carbon cycle than what we had. So first going to list the components which we are ready, basically more or less ready to go in, and we anticipate being able to go into at least a leading group of models. Maybe we sort of said up to 6, but that's not a very well educated guess on the number, at least from my point. So ocean biogeochemistry with a simple ecosystem model, where the simple ecosystem model refers to something called NPZ, which is nutrient, phytoplankton, zooplankton representations. The terrestrial carbon cycle model, typically the standard would be without having any nitrogen limitations in the model, and probably including some sort of representation of at least natural fire. Biogeophysical models, of course, of water and energy exchange, which basically all the models already exist, but these two things have to be need to be taken in tandem. They're going to be developed sort of together, the biogeophysical model and the terrestrial carbon cycle model. So in terms of vegetation dynamics, expect that there'd be a relatively simple version of the vegetation dynamics, which would basically include at least some sort of age class succession processes, using limited plant functional types like order 5 to 10, not the more advanced versions that George talked about the other day. So a simple succession, and a little bit unclear exactly what all the models will do about sort of dynamic biogeography. So models that might be a bit of a point where not all models agree. And of course, Peter, you weren't here this morning, so step up and say stuff when we say something wrong.
I'm not sure I know that term, even though I might have heard all about it, but I didn't remember. What is dynamic biogeology?
Geography. That's basically just allowing vegetation types to move, the distribution to move over time, to change over time in response to climate.
Dynamics.
Well, yeah, slightly separate from veg dynamics, because just the sort of the regrowth of a forest at a single grid point, but not allowing maybe things to redistribute themselves.
It's a component of vegetation.
It's they're maybe not all models will be able to do both.
I think veg dynamics normally meant to be all of those things.
I agree that that's what it's normally meant to be,
maybe
but
we
the
just
question
need to be
is
explicit
whether
that we're talking about both. Yeah.
we're talking about both, but we did raise the point that we're not entirely sure that all models will be able to do both. Yeah. So it's a little that's a bit of a, I think that's still a bit of a fuzzy one.
I think the other part of that discussion was that over the 1 to 100 year time scale, the succession is much more important than the geographical redistribution, probably, because the geographical redistribution tends to be slow.
But I suppose, sure, but okay, I mean the succession is just local veg dynamics.
Yep.
Right, and the way these models work is at the moment, they don't do anything like seed dispersal. They just seed every grid box individually, so the veg dynamics
exactly.
and,
that's the difference.
And the succession are the same thing at the moment.
Yeah.
I mean, you could see a situation where you were not doing dispersal in a model that did dispersal, but since they don't do dispersal anyway, the veg dynamics is the same thing.
Right. I guess that's a good point. It's sort of whether you have dispersion, you're trying to include dispersion.
Sure.
Maybe that's the cutoff.
Cool. Yeah.
Is there a time scale question here?
We go to get down a time scale, and we answered that one probably poorly. I think we'll get a bad mark on that. And so then anthropogenic land use and land cover change. And I think the point we wanted to raise here is that, well, this one's, I think, very critical if you want to get the carbon cycle to close the carbon cycle. And the point here is transience. And I just want to make this point because we've always been we've had the ability to do a land cover change experiments for a long time. What's more, the newer thing is to be able to have a transient land cover change. At least that's definitely the case at NCAR, and I think it's true elsewhere to actually have to be able to deal with transient land cover change. So, and that's obviously going to have to. The important thing is to translate scenarios of land cover change into the carbon fluxes, and that's going to be a key aspect.
So you just lay that on top of the vegetation dynamics, right? So you just
Yeah, that's right. It would be sort of a controlling factor for the vegetation dynamics. Yeah, boundary condition. That's
Or
what.
if you look at the recovery after, like, cropland abandonment and a lot of suggestions.
Is there other things to land cover change other than land use change? Are there other reasons?
Fire.
Fire.
We're talking about fire.
Thanks.
And then
Well, changing climate is a DGVM job. So yeah, I guess fire is one. And then the last thing is land management, some form of improvements in the way we treat land management, and this is close to the leading edge, I think, here. So agricultural activity on cropland, irrigation, and forestry. So trying to get a representation of that into the model is what. So that's basically the list of things that I think we decided is most of these things are ready now and could get into the next core version of ESM with a significant number of models.
Sorry, small correction about the first bullet. Maybe it's better to say NPZD more.
Yeah.
Okay.
With detritus.
Okay.
Yeah.
So,
Yep, I'll add that in to try.
So just to follow up something Dave just said, I think George mentioned this a little bit the other day, that when you think of land use change, you're thinking of agriculture to urban or forest to agriculture.
Mm-hmm.
But apparently it can go back, there's some that goes back the other way. Agriculture could go back to forest.
A lot.
Yeah.
And that's a lot?
A lot.
Really?
U.S.
In the tropics especially, it's a lot. But also in the U.S., the whole eastern half of the coterminous U.S., that's where the agriculture primarily was prior to 1900.
Yeah.
Then it all moved to the middle part of the country, and that created the forest regrowth in the eastern forests. So that was sort of a one-time deal, but that happens routinely in the tropics through shifting cultivation.
Yeah, Harvard Forest is all agriculture
Oh, yeah?
back in 1700.
Huh. So, I mean, with increasing population, wouldn't there be more demand for agricultural cultivation? Kind of
Generally
global?
speaking, yeah.
Yeah, so the total area will go up.
Generally speaking,
Yeah. So you'd still have some areas that would be going back the other direction.
But there's a historical element to this as well, particularly the regrowth stuff, which means that the land use change from way back is influencing your carbon sink now.
And then you kind of have the slash and burn phenomenon too.
Right. Yeah.
Just you have to abandon it because you're not getting
Right.
your production.
Right.
How serious is this land management predicted in the model? Like, for example, how is the availability of fresh water?
I'll leave that to you guys. We don't do it in CCSM right now.
You mean irrigation?
Yeah. Like, are there restraints on freshwater usage based on a real availability of fresh water for irrigation, things like that?
Well, it's not done yet, so
Right.
not, but you'd have to do it that way, I think. You'd have to, because in order to do it internally in the model, it wouldn't make sense to do it unless you're doing it with some consistency.
I think irrigation will be a stretch to get in the core, actually, but some of the models will have that. But then it's a closing of the water cycle problem as well.
Yeah, we've been already starting to think about that and whether it's going to come out of a aquifer type thing or whether you're going to pull it out of the rivers and things like that. It gets a
The
little
land
complicated.
management there is largely prescribed, isn't it? We're not going to do this interactively in the models.
That's right.
So it's prescribed. So the issues to do with whether there's enough water or whether there's a demand for agriculture will be done offline by other people who will provide scenarios.
Well, if there's enough water, you would need to come from the model, right? Somehow.
There's an issue to do with the consistency of the scenarios that I frankly don't think we can do it on that time frame.
Okay. Yeah, this land management may really
Yeah.
not belong in here. There'll be some of these things will be healthy treated. Forestry may be easy.
Well, a good example of what will be in there is, for example, cropland. If you have to sort of, the simplest version would be to plant grass on cropland and cut it every year so that a forest doesn't regrow there. So that's the simplest form of land management that you'll see in there.
Yeah, we already do that to some extent.
All right.
Farmers are anti-foresters.
So we've already talked a little bit about this, but we raised a number of issues that we're facing the modeling groups to try to get this kind of a model ready by the next by AR5. Basically, it's going to require that a lot of these models exist already, but require the integration of the carbon cycle model, land use, land management, and DGBM capabilities, and it's not necessarily trivial. For example, I talk a lot about NCAR because I know, but the DGBM and NCAR that's been developed is sort of has some different fundamental structure to it than the carbon cycle model. So there's going to have to revisit a little bit about how that goes, and these things always take time. So just saying that we're all going to put these all together, maybe sound easy, but it may not necessarily be as easy as it sounds in all cases. And also, we're bringing this up here, and this is an obvious point, but we're going to bring it up a couple times. Is that, of course, the terrestrial carbon cycle, in particular, depends very heavily on the climate simulation. So as we mentioned earlier, there needs to be a set of metrics that you can give to the developers of the physical model that need to be met in order for there to be a meaningful simulation of the carbon cycle. And there's something known as a Koppen classification, which even though I was explained to this morning, I still don't quite understand what it is, but it's...
Yeah, it should be.
Oh, it's KO. See, that's the extent of how little I...
Just a biogeographical thing where you take what's the climate space thing actually.
It's like a Holdridge diagram.
Yeah, it is.
Basically, potential evaporation versus precipitation.
Yeah, sure, to work out, roughly speaking, the biome.
Exactly.
Well, that's what.
So it's not adequate for a physical model, except for Dave. Yeah, not for me. I don't know what you guys are talking about yet. So if you want to elaborate a bit, I appreciate it.
Well, Ron was talking about that you were using a Koppen. You have a script that basically calculates.
All the input for Koppen is monthly mean temperature and precip at each grid point. And so it's easy to develop a script to produce classifications. And in a large scale sense, if you have a dynamic vegetation model, that's the kind of vegetation that's going to be produced if the model's doing the things right.
It's like a diagnostic sort of.
It's in some sense it's just a filter of the model data. It's another way to look at it.
Non-managed systems.
Yeah, but it just comes out with like 10 different types of vegetation that could be produced for that given precipitation and temperature regime at that grid point. And you pick one of the 10 that fits that. It picks one. So you get a
It's
distribution.
empirically based.
Yeah.
I mean, it's based on today's climate.
Do we have something like that sitting around at NCAR right now? Or is that?
I don't think so.
Ron says we can borrow his.
It's easy enough to do, isn't it?
Yeah, I mean, it doesn't sound
just
like rocket science, but I think it would be very useful.
Yeah, I mean, it's very good also if we kind of adopt this across the board so that we can compare GCMs prior to the coupling actually in terms of that sort of classification
And
system.
we're using it in-house as a way to make sure that the dynamic vegetation model is behaving itself. Because in principle, it should produce something that looks like that classification.
We were going to use it.
So you mean if you feed in like a reanalysis product of temperature and P minus C, then you'll get
something that looks like natural vegetation.
like today's world.
Assuming the natural vegetation is in equilibrium with the climate.
Yeah.
But you do.
That's
And you
good.
do that.
It's a lot closer than most DGBMs, let's put it that way.
But the other interesting thing that Ron was telling me is that, we worried a lot about, if it's raining in the wrong place, we'll get the wrong vegetation growing. But he says it's actually not quite that bad because the land surface scheme is kind of a filter almost, and so it doesn't it may not be as bad as you think. So even if you did, if the vegetation could move around, and you think, oh, we're getting a lot of rain over the Sahel, so it means we'll have tropical rainforest way up into the Sahara. It may not actually produce that, because if you run it through this Koppen script, it'll show you what it's likely to produce.
Sometimes you may have an error in precipitation that's cancelled out by compensating error in potential evaporation, for example.
Right.
Yeah.
That's exactly right.
Yeah. It's always good if you get the right answer for the wrong reason. Gives you more chance of getting the right answer.
But the Amazon's hopeless. You got to get the precip.
You're going to need lots of aerosols there.
There are lots of precip.
The I think it's NRL has a code that computes the Keppen classifications.
Oh, like I said, I think the guy that did it, GFDL, did it in about a half hour. So it's not like
Fiorito did it for all the CMIT models.
Okay. Yeah. So that's the one we have inside at the lab. It's a ferret script, if you know what ferret is, which is a analysis.
But the flip side to using it to as a check on the vegetation models is it's a check on the climate models.
That's what it is.
It goes both ways.
Yeah, exactly.
It's mainly a check on the climate.
Depends if you're a climate model or not. From my perspective, it wasn't.
Right. Cool. So it sounds like that might be quite a useful thing to be encouraging groups to be using. And then just raising the point that when we do couple all these things together, it's quite possible, if not likely, that we'll get some surprises. So time is of the essence. This was obviously something that the CCSM community is aware of, and that's why we're, as a group, trying to couple as early as and often as possible, as Phyllis sort of mentioned a bit. And I know that Ron doesn't you don't believe in this that coupling as early and often as possible is that critical, except for to look for bugs. So that's a bit of an issue. But anyway, it's just raising the point that you could get some surprises. And this last one, we didn't fully formulate exactly what we're talking about, but we're wondering about the situation where if some models want to be in this class of models, but can't quite get all the components together, is there some sort of information that could be provided that would essentially make up the difference, so that the models are essentially almost like these more advanced Earth system models? And this is just an idea that we just sort of started talking about, and I don't know if we need to talk about that more right now or not. But just like prescribed land cover, if you don't have a
I don't think you'd want to be to limit people from being involved in these kind of exercises just because they didn't have to have photodynamics ready.
That's sort of exactly what we were sort of getting at. Yeah. So it's probably that's the one that it seems to me that it's not clear everyone's going to have, and whether or not they need to have it. Photodynamic.
The key thing is that we're proposing to close the carbon cycle, right?
Right.
With
right. So if you prescribe the succession of your forests, then that could be adequate.
Yeah.
But, I mean, how are you going to do that and still close the carbon cycle?
I just saw that.
Do well.
I don't think you can not have vegetation dynamics and still close the carbon cycle through some kind of prescribed something.
Well, it's already done. The vast majority of the seafoam.
Well, you can close it, but close it wrong, incorrectly. So.
Well, yeah. It's one of many errors, George.
Okay.
Okay, and then so this is a bit the same as the chemistry and aerosols group did. We called it actually the vanguard. So it's sort of things that may be in a few models, but more likely it's something that's for the next phase or next cycle of IPCC. And so there's a fairly long list here. I'll just go through them. Putting nitrogen into the terrestrial carbon cycle, which some models may have. By this version, fire. We didn't talk really as much as we probably should have about fire, but we said earlier that we expected some sort of natural fire to be in the Earth system models, but maybe human management, the impact of human management on fire may not be incorporated into most models, but could be in the future. River biogeochemistry, so the sort of how inorganic carbon, for example, can get transported out of the system. Yeah.
On the human management. I mean, isn't that the kind of major control over fire? is management, human management?
It depends where.
I think in Canada, you're going to have fires whether humans are there or not. Or Siberia for that matter.
Yeah, high latitudes.
Human management is actually a small fraction of total
Fire.
It's a less
It's a
traffic.
big deal in the US.
I wouldn't say it's a small fraction. I don't know if we know the fractions. That the tropics have a lot of most ignitions are human caused in the tropics.
Yeah.
And in the temperate latitudes, the big deal is fire suppression.
Right.
If you get to these boreal or high temperate latitudes, it's more or less wildfire, I think.
So you can have fire in
Yeah.
a lot easier than trying to quantify the human management part of it. So that's why you're saying the human
Yeah, it's
management.
fairly easy, I guess, to do the natural fire because you can just based on climate variables.
It's hot and dry, and there's lightning.
Dry, yeah, exactly. Yeah. I suppose you could ask the question whether it's reasonable to do any fire if you're not going to do all fire. That would be something you could ask. Micronutrient limits on ocean biogeochemistry, for example, iron fertilization, and ocean bottom carbon chemistry. I guess calcite formation. This is something that's only going to be probably important on longer time scales than for the most part that we're talking about. Not CC,
Stabilization.
but maybe important for stabilization. Yeah, yeah.
Can you elaborate on what that means?
I'll let elaborate.
As the ocean takes up anthropogenic CO2, the ocean water is acidified with lower pH, and that pH makes the finally the bottom water more acid, of course, and in that situation, calcite is subject to solve in the ocean, and that makes finally the surface PCO2 lower, and that effect can be important on a time frame of 1,000 years or so.
So then, reactive gases, for example, methane or VOC sources from the land is probably a vanguard at the moment.
What's the limiting technology? What would prevent you from being able to do that in the non-vanguard simulations?
I'm not sure.
It is already in the CLN, the VOCs, not the methane.
Right.
Methane, I would think it's a wetlands problem.
Yeah,
I would
with
say.
wetlands, but then
You can do that.
Does
the
it
housing
exist
center
in
model
wetlands?
has wetlands,
Yeah,
so
there are
principally you could do it.
And I think you can do that. There's no point to do it unless you can accomplish atmospheric chemistry, though, isn't it? It's only a diagnostic thing.
Well, the VOCs, yeah, we care about.
So it's one of these things you would do if you're coupling, because you have the CLN, otherwise you wouldn't bother.
Right.
Because the carbon loss is small compared to the rest.
So do you think this should be actually moved into?
How about as an
One of the-
option if you...
Well, all these things are options. Really, anything in this Vanguard list is if your model was able to do it and go above and beyond the core, I think that.
Yeah, but what I'm
strategy would
objecting
be
to is putting it into the Vanguard section rather than putting it into
Okay.
the other one as an option.
Okay, we
So-
can put it in the other one, saying brackets, if you're coupling atmospheric chemistry.
Yeah.
I think our other section was designed to be, this is my take on this. We were saying that there's probably going to be half a dozen models which are defined as sort of the new mainstream Earth system models, and we were trying to define the properties that we felt that they would have.
No, well, it doesn't go
It wasn't a wish list, it was just the properties they would have. And that some models would have some elements of this list.
Okay. Yeah, that sounds perfect.
And a more advanced EGVM with an improved succession due to more species in the Vanguard.
But that do you mean
Topic.
to include in dispersion, vegetation types changing independent of succession?
Not unless you have a very high resolution atmospheric model, I think. I mean, what are the length scales for dispersion, George?
in most GCM grid squares, I'd imagine it was all within grid square, isn't it?
Yeah, but you're going to obviously have to have between grid square dispersion too. You have to parameterize that somehow.
It'd be tiny.
Yeah, but sure. I mean, in principle, it's possible to parameterize the dispersion across grid cells so that it would work in the coarse resolution model similarly the way it would work in the fine scale model.
So possibly.
Yeah.
More species definitely, possibly dispersion.
Yeah, but I think going back to the previous thing, I think most, at least the groups I know of, aren't really focusing on that between grid cell dispersal problem because we're thinking that succession within grid cells is really the big story.
I think it will be, won't it, as long as the grid square is big compared to dispersion length squares. We get the high resolution, we'll have explicit dispersal going on, but I suspect that's the 10 kilometre scale stuff.
Right.
I think so.
Yeah.
But if these climate models are still at 2 degree or 1 degree or something like that.
Or what we're going to be at, Jerry, then half a degree at most.
Well, yeah, at most.
Okay.
More like 1 degree. Or,
Yeah.
or a core more coarse.
Be 2 degree.
Yeah, for ESM maybe 2.
Maybe 5 in our case.
Well, ours is going to be 2.
You don't have to worry about it for a long time then, huh?
Dispersion.
Yeah, so this is definitely a vanguard, I guess, issue. Some sort of transient urban land cover. We're sort of thinking that there's already tiling schemes and groups can choose whether or not to include urban into their core model. It's probably not that important, but urban may become more important in the transient sense if the urban area does expand dramatically. But that's probably not going to be a core aspect of the model at this point. I think also just because it's not that important an issue, or we don't consider it to be that important of an issue to invest our resources in that. Possibly a higher resolution land surface scheme where we can sort of improve the explicitly, doesn't make any sense, improve the explicit terrestrial processes. And this is something that it could be non-regular grid, like a basin scale catchment, or just high resolution. So that's something that at least NCAR is working towards, and we will probably have something ready by AR5, and whether or not we actually use it or not will be a decision by the SSC, I guess. But and then the impact of ozone on vegetation. So I think that's a fairly long list. Is there anything else that anyone, I guess, Peter, that you want to add that you don't see in here that you weren't here this morning?
Very coherent way to summarize very
incoherent discussion.
Especially considering I'm not
Must have been better when I wasn't
neither
there
a
this
carbon
morning.
cycle model nor a
We made
GGBM
tons of
model.
progress this morning.
You're the right person to do it.
Yeah.
This is sort of a subset. We have river biogeochemistry and ocean geochemistry.
Yeah.
Did you mean to include lakes in with the rivers?
Yeah.
Yeah. I guess so. That's how we
Fresh water.
currently.
Why? Why do we care about that?
Freshwater lake biogeochemistry.
I mean, the issue with the river stuff is to do with the carbon transport from land to ocean, right?
Yeah, but some of that's going to decompose, and if you're running rivers into lakes and out of lakes, you're going to be decomposing and actually adding carbon from lake production too.
Okay.
If you care about lakes, then you should care about dams.
Yeah, exactly.
Oh, definitely. I mean, it's like
that's,
I think it's
land
half a
management.
petagram per year is being
Now you know why
stored
it's
in the freshwater
Vanguard.
system. So I think it's mostly on solid.
Vanguard squared. Maybe cubed.
Does it ever come out?
Yeah.
Ever?
Yeah. I mean, if it's just sitting down there in the bottom of the lake.
That's a net accumulation right now.
There's
By
a
half
missing
a
thing
petagram.
there.
Yep.
I know I'd come up with one. Organic soils.
Yeah.
No one does
should
organic
put-
soils properly, do
should
they?
put that in there. I'm
Yeah.
working on organic soil.
What do you
Left
think?
my own thing off the list.
Okay.
Organic soils. I mean, obviously there's soil carbon pools that are part of the cycle, and part of the carbon cycle, and could have given a talk on this, but what we're trying to do is to take those organic pools and then apply them to the physical properties of the soil in terms of the hydraulic and thermal properties of soil.
Yeah.
So it's important for high latitude.
Composition models are all basically transfers from mineral soils, and then we
That's
apply
right.
them. And the most important areas are the organic ones. They're not really designed for that.
That's right. Yeah. Yeah, this is very critical, of course, in the high latitudes. It affects the thermal structure of your soils a lot. So, yeah, actually, I should add that to the list since we're actually working on it.
Something else which is potentially missing from your list is N2O emissions from soils related to agriculture.
Yeah, sort of kind of with the nitrogen cycle.
Yeah,
that we were talking about.
So you
but this is that's a
limitation.
Yeah.
Nitrogen is the white
Or
cells.
carbon nitrogen interaction, basically.
Yeah.
There's a lot of reasons to add nitrogen, including that one. I mean, the other big one is that's at least many people believe that's the going to be the main sort of limitation on CO2 fertilization. So without that, most models are probably going to overpredict CO2 fertilization.
Yeah, that's kind of why I was surprised that you had this on the Vanguard list, because that seems to be a pretty critical.
Well, it's really critical. The problem is it's not easy. So in the next year,
we've been trying. Get them to do it.
Well, I think half the models will have action by that time.
Yeah, I think we just came across this point on a number of these, is that whether they should be in this Vanguard section or, like you just mentioned, an optional part of the core. What does it mean that it's sort of they're both fairly mean the same thing?
The nitrogen ozone, potentially cut into the chemistry as well.
Yeah. So all these things become a lot more important if you have a chemistry model in the atmosphere.
And I think too, when we delineated between core versus Vanguard, we sort of made the assumption that if it's not being implemented right now, it's probably not going to be core for AR5.
Yeah.
And so not every model is implementing nitrogen. They're getting carbon in there, but not necessarily nitrogen. So that was sort of the logic in the split. And it's all relative to AR5 and beyond versus now. So
sure.
Our time scales, as with the previous group, were sort of collapsed a little bit.
yeah, I mean, you heard Ron say he's not going to look at any new updates of the LM model for AR5.
Ever.
He doesn't have nitrogen yet, so you're not going to have it.
No, I wouldn't say that. I would say that I would characterize it if we get a working ESM soon, then you can start adding stuff to it. But if you don't have it soon,
I have some more time.
Then it limits how much more stuff you can put in it.
Yeah.
Right.
Until you get the thing working, you don't want to be adding anything to it. I already have enough problems.
I think that some of these are related to which came up with the fire. Like you made an interesting comment that if you're not going to have the human management part, you might not want to add fire at all. I think nitrogen is sort of like if you don't have the land use component, you're not going to want to bother adding nitrogen probably because we've doubled the nitrogen cycle through agriculture, for example.
Right.
So you're way off if you do nitrogen without land use.
So you putting in a natural nitrogen cycle and no anthropogenic emissions would be a double bad.
Yeah. Kind of like putting in wildfire without the human management on fire.
I guess that's going to require some consideration about how exactly how to deal with it. So, it could cause problems at NCAR if that was the directive. I think. I don't know.
But
If that's true.
The nitrogen deposition bits, once you've got a nitrogen uptake module,
Yeah.
nitrogen deposition bit's quite easy as long as the chemistry.
Oh, that's right. Yeah, if you, that's right. Actually, maybe it wouldn't be a problem.
Deposition's pretty easy, but fixation's hard.
Yeah. You'd have to do that anyway, wouldn't you?
You have to do that anyway. That's true.
Okay. Moving on. This is a question about coupling frequency. And I guess unlike the chemistry, there's not really an opportunity to do anything other than synchronous coupling. I don't think in the carbon cycle model, although there might be a hierarchy of updates at least used in a DGVM, daily to weekly for phenology, monthly to yearly for dynamic biogeography. But I don't think this is going to severely impact the costs. It might just be more philosophical than anything else. So basically, synchronous coupling.
I'm just, it's quite important because basically what we've implied is that the fluxes are calculated in the land surface scheme. We don't see the flux, even the carbon fluxes, as part of the DGVM, they're part of the land surface scheme. Yeah. So they're calculated every time step.
Yeah, that's right.
Yeah. The
So
CO2 fluxes.
the CO2 fluxes are synchronously coupled in.
Yeah.
And you could accumulate those fluxes for a while and then apply them to using in your phenology scheme or your dynamic biogeography. So then this is the one that maybe we need to think about more carefully. The time scale of feedbacks, DGVM from 1 to 100 years, which doesn't really help help you very much. As long as you're not trying to just do a weekly forecast, you need to.
What feedbacks are in 1 to 10 years? Grassland in the Sahel.
It's,
I mean, it
some
only be
succession,
grassland.
I
It can't be forest, obviously.
There isn't much grass in the Sahel.
No, sometimes, I swear.
If you burn the forest, then you have
But I almost think that the important point is what we actually talked about with the carbon cycle is that you could say that maybe over 10 years there's no global feedback, and the carbon cycles may not kick in globally for 30 years. I'm not sure if that's the exact number, but in any case, these biogeophysical feedbacks can occur and regional feedbacks can occur on a short time scale, and it's difficult. One of the attractive features, for example, about a carbon cycle model, whether it's coming out of your DGVM or your carbon cycle model, is that you have a realistic phenology that's forced by the climate. So you get interannual variability in your vegetation characteristics. And so, if you just turned off your carbon cycle model, you would lose that. With those things may be important for the climate on even 10-year timescales. So it's not, I guess at the end of the discussion, to me at least, it wasn't clear that you would run into situations where you'd say we might as well just turn the carbon cycle off. But I think that's open to a bit of debate. It depends on how your carbon cycle is.
Yeah, it depends whether you define the phenology as part of the carbon cycle. Right. Most phenology models are sort of independent of the carbon fluxes, strangely, but
right.
But I think we're talking about sort of these models are sort of coming together as these integrated sort of land models where you're doing
the carbon and the physical properties and the biogeography all together.
DGVM.
Yep.
Yeah.
Okay. In that case, I agree.
And then it becomes hard to, once you do that, that has a lot of advantages doing that because they all are mechanistically related, but it's hard to separate them.
The next assessment report, though, we will still have phenology that's climate related, I would think, rather than anything more sophisticated.
Yeah, that's climate related, but it's
plant functional type dependent also.
The carbon fluxes are contributing to the actual rates, right? I'm not sure.
Something we didn't talk about that I just thought of is under a timescale of feedback, you can have a very short feedback with a vanguard type of implementation of extreme events. Flooding, hurricane, massive wind throw, massive fires. So if you had a sort of extreme event, and this might also link into the climate models, you'd have a very short response on large scales.
Yeah.
Or lots of small scales. That's a question. That's a
certainly
question with
natural wildfire.
hypotheses for.
I mean, you raised the issue. Do climate models really give you flooding events?
Well,
sure, there's river water, but does that ever overflow riverbanks in models? I don't think so.
Sea level rise. I mean, I don't think they're doing. I think that might be a vanguard for a climate model as well. Is actually getting at extreme events.
You could certainly get a fire event.
Yeah.
Even in the existing
We don't get flooding.
No flood on purpose.
No flooding.
They don't rain right now.
No, it's not that. The rivers don't flood.
No.
Sea level rise.
You can diagnose it though.
Yeah, but the sea level rise won't.
Well, that was one example. Flooding and sea level rise.
Hopefully it won't.
depends on your ocean.
Yeah, if you have a free surface, you'll see
So basically,
storm.
disturbance processes can be fast.
What you don't see is storms with higher sea levels driving the water further
Well,
inland.
storm surge.
Oh.
You won't see that.
I wasn't.
No storm surge.
No, I wasn't thinking of that, but I was thinking in terms of a future, what might be a vanguard type thing to put in there, or that would show these fast responses that would also link into the very last thing we talked about, which are observational data sets. And if we're trying to evaluate our models relative to what, say, the remote sensing data is telling us, and the remote sensing data is telling us that a whole island is burnt or something, and our model's not capturing that, that might be something, these extreme events might be something to think about. And this also might tie into the short time scale experimental design that we'll talk about tomorrow. What sorts of, things can we think about looking at for short time scales?
But in terms of the DGVM, it sounds like this phenology
happen pretty fast, right? I mean, you
Sort
can
of
kill vegetation in a matter of years, but to get the vegetation tight and move around,
That takes more time.
that's more time.
That's at least decadal.
Right.
But you see a response both in the vegetation type and the carbon cycle immediately after an extreme event like that. You
Yeah.
see a huge switch
So-
from, say, a positive flux to a very, depending on whether
I mean,
it's acid or
generally speaking, the disturbance processes are fast and the growth processes are slower.
Yep.
So anything that involves loss of the vegetation, you think, well, the impact on climate could be very quick.
So in general,
There's an asymmetry.
the time scales could be short.
Yeah.
And fire
There's an asymmetry
or
in the
drought-induced mortality are probably the big sort of candidates for that.
To get river floods, I mean, the hydrologic service has trouble doing it. It would require much more details in terms of your river flow than GCM's ever considered doing.
Yeah, you probably have to go to the basin scale approach to modeling your land surface before you really be able to have
scales,
floods, and groundwater tables and things like that. Yeah, that's a. I don't know if that's not really a carbon cycle GGVM. That's just a vanguard issue for models in general. Yeah, for land surface models.
Yeah, I think
it's
the
probably being
GFDL
considered.
model is not probably nothing about this, but they've got the rivers running on a separate higher resolution grid to try to do some of the river routing and things like that. I don't know if they're doing floods.
We do too, but it's nothing like enough. It's nothing like enough resolution to do a flood.
Comes out of those grids, it goes in and just slides right to the sea.
Yeah.
That's right. It's not,
Might be a
it's
lag
not
or
in the
something
system
on the
anymore.
way. It goes.
There are attempts to do that with models that begin to put water tables in, but I don't think we don't really consider those part of the DGVM model. That's a separate hydrological thing.
It's a physical model development,
And they're coming.
which we could exploit. I guess the carbon cycle model could exploit at some point if it ever happens. Computer resources then?
Cheap as chips.
Cheap, yeah. We had a discussion, we couldn't exactly figure out what exactly the 3 to 5% increase that you're talking about. Is that to the land model? Is that just adding the carbon cycle model that you mentioned?
That was
To the-
terrestrial model to a atmospheric mixed layer model.
Okay. So
And that
that's
includes
very,
carbon.
it's
That's
very
fairly cheap.
inexpensive.
It's very cheap.
I would have guessed that.
The other way to look at
Which
it, the rest of the model's pretty expensive.
Yeah. Well, that's what we did in the past. Is we waited for the rest of the model to get so expensive no one noticed.
Which is the way I would look at it.
So you look at the bang for the buck, it's huge.
That's right.
I remember a slightly higher number for CCSM, but I don't remember. Do you remember? It came up at the 30%. So anyway, it's relatively inexpensive compared to some of the other things we've been talking about. For the terrestrial carbon cycle, the ocean although there is an issue related to storage, there's quite a few more prognostic variables which need to be stored. Quite a large number of increase in prognostic variables. So that's actually going to be, that could be an issue.
There are 2D fields.
They are 2D fields, yes.
Or small
Yeah, that-
3D fields.
What's that?
Or small 3D fields.
Or small 3D fields. Yeah, some of them have some. Yeah, so that's right. But I guess that's right compared to what the atmosphere model does. But this is going to vastly increase what the land model requirement is. So maybe that's just where we're thinking in land model space, where it seems like, well, that's a lot.
But you need to save them all?
Some of them probably for to diagnose how your model's doing, I presume. But I don't know if you need to save them all in a operational run. Probably not. I don't know how that works. With the ocean biogeochemistry is more expensive. Estimate from you have a 2 to 5 times cost to the ocean model, mainly due to a large increase in the number of tracers. And the same issue with storage.
How many is large increase?
Well, it scales roughly with the number of traces. So 2 means doubling the traces and 5 means 5 times the traces.
I thought it was doubling the cost. Yeah. So you said the ocean biochemistry is the same as the ocean.
Yeah, that's right. So
Yeah.
the ocean's double as expensive. Even in these simple ecosystem models, you could easily make it 5 times. I can write very inefficient code.
You could easily do that.
That's where you get the big work.
You work hard to make it
academic, right?
So you justify a new supercomputer.
So anyone have any more comments on computational costs?
Those two sets of stats are a little bit apples and oranges, right? I mean, to go to this next level of the terrestrial models, we'll increase the terrestrial model alone time by factor of 10 probably. It's just that the terrestrial model time is a small fraction of the coupled model time.
Right.
So similar with the ocean model, you're going to increase the size of that 2 to 5 times, but I don't know how big the ocean model.
Oh, it's extremely important.
Well, it's extremely expensive.
It depends on the episode, but if you do 2 by 1, it's 35%.
Yeah.
The ocean model is 35%.
That's a 285 by 1. Yeah, it's a lot less. But
so if you double
because you're running like that, the ocean group, so we should be a bigger percentage. We'll put more vertical.
Well, here's your opportunity to get up in there. And get, if you have this, you get together.
CCSM, it's 2 point something. The ocean ecosystem model.
Right. Okay.
And I think it's 35 traces.
35 traces.
That's pretty efficient then.
Okay, scenario requirements. Basically, I think the biggest thing is having a consistent land use and land management scenarios. Gridded information is going to be required, and this is a bit what I think this came up a bit in the chemistry and aerosols talk is about. Well, the disturbance history is required, and I guess that's not the standard way that they run their scenarios as they run them out for the future. So I'm not sure whether we need to ask them to reconsider how they do that, because preferably you'd have a smooth transition from the past to the future, which would include this disturbance history and some representation of future disturbances, I guess, as well. So I guess that's a big topic. Anyone want to comment on that?
But that's
beyond
disturbance history. I mean, you still only need disturbance during the period of the simulation, don't you?
I mean, from 1850 onwards, or do you mean prior to that?
I guess George could answer whether we need to have disturbance prior to 1850.
The further back you go, the less you need it.
Yeah.
The land use history we just published goes back to 1700.
Okay.
But I bet that it doesn't really start to matter until 1800.
Okay, so, all right.
Yeah.
It's a question of as you were suggesting, question of consistency between the historical scenario and the future scenario.
That's right.
In terms of what they're providing to you.
Yeah.
Can I ask a kind of a related question, which is just that I sort of remember conversations about the carbon cycle models taking 1,000 years to equilibrate in order for given a new scenario. So is this essentially equivalent to if you go far back, then you don't need to? I mean, is it in essence is the disturbance history providing you the initial conditions which are at equilibrium for a given?
No, you still need to get the model to equilibrium with the disturbance history. I mean, the issue is that you're looking for a rather small signal in terms of the net uptake compared to the gross fluxes. So you can easily wash it out with the drift particularly in your ocean model, also in your land model. So the issue is getting to some equilibrium with whatever your disturbance history is. In the case of the ocean, it's just a question of getting the flux to near zero net. It takes a long time.
So have you guys figured out any acceleration techniques?
Yeah.
Because I don't think we
You have to do them.
This, do we?
You have to do ocean.
Well, Peter has some accelerated techniques for the land. It still takes a long time, but there are some.
I mean, that will be a big part of our discussion tomorrow. I think it's something that limits, in some ways, the sophistication of the model you can use, because the spin-up time in terms of CPU becomes potentially much more than the scenario run.
But there are some published analytical approaches for getting at least the century class biogeochemical models analytically estimate their equilibrium conditions without having to literally.
It's relatively easy. Yeah, I think it's relatively easy with terrestrial models. It's much harder in the ocean.
Yeah, that could be. I'm not thinking about the ocean.
This is actually a good point now for computer vision.
I was just going to say it. In fact, I was thinking yesterday that was
not only how much does it cost to run the model a year, but how many years do you have to run to spin up things like that. So
Right.
There are additional costs there.
Yeah.
But you just
I forgot to
have to
mention
spin it up once, though, right? I mean, you decide on what your initial state is, and you run it.
Well,
and
you spin up every time you change the model, though.
That's right.
Every
If
time
you're
you
trying to put a carbon cycle in, then you're trying to get all the final parameter values or whatever. You have to do a number of runs.
It's like equilibrium runs for the ocean. You run it a long time, and then in year 800 it blows up. You have to go back and start over again.
Yeah. So this is essentially the issue which I think was raised at the CCSM meeting, is that there's some concern about leaving everything to the last minute because the process of fixing things could be very slow. Right? Slower than last time, yeah. So this is a bit of,
That's a model development issue, not an actual running the model. I mean, once you get this sorted out, I mean, it'd be very painful, but once you decide on what's in it, you run one spin up, and then you run all your experiments off of that same initial state.
But it's quite often, particularly if you're using more sophisticated ocean biogeochemistry, it just wouldn't be feasible to run 1,000 years. So you would have to spin up your physical ocean model and then diagnostically spin up the biogeochemistry if it was expensive. Because the biogeochemistry, the expensive bits of the biogeochemistry are short time scale, actually. So you only really need to know the physical state is in a good balance, and then you can diagnose those.
It's a good thing that biogeochemistry models are cheap.
Compared to physical. But for the last assessment, we did not do any equilibrium ocean runs. We always started runs from Levitas.
Yeah, can't you do the same thing with carbon? Equivalently start and hope that your drifts are small?
You could, I mean, very unlikely they would be.
Make it lucky. I mean, people do all the time with Levitas.
Well, what you do though, what's happened in that case? Sure.
Excuse me. What you have to do is assess the drifts.
That's right.
And then, when you're doing the projections, you have to take the drift from the control runs out.
That's correct.
That's what you have to do.
That's the game, and I'm wondering why you can't do a similar thing with carbon.
I think it's because the fluxes are dependent on very large, slow stores. I mean, what you do in a climate model is, the way things have changed is we used to spin up the ocean forever and say, well, it's got to be an equilibrium state regardless of whether it looks like Levitas or not. Now what we do is we tweak largely the atmospheric model, don't we, to make sure it is in equilibrium state with Levitas. It's harder to do that with I think it's harder to do that with the ocean biogeochemistry because I think the process is so much slower. Not to say it's impossible, but it's not the way we've done it in the past.
Right, well, I was just, I'm poking at people inside GFDL with the same question, and I haven't really got a good answer.
Do you have enough observations to tell where the carbon is?
Yeah.
There is. I mean, there's a gridded data set that you can initialize an ocean.
A 3D data set of carbon.
The equivalent.
But if these transients that you're then subtracting out are large, that becomes worrisome.
That's right. But one can make the same argument people do with the starting from Levitas, that the model in principle should have small drifts.
I agree. I would.
We're very principled.
This is something
it never works that way, but in principle should.
We'll have to discuss this tomorrow morning. I think this is a big issue, spinning these things up.
I don't know what you plan to do with any of this, but you could make the point that computer resources really should include model development costs too, not just model running.
Yeah.
It doesn't make any difference how long it takes to run it if you can't develop it.
Yeah. Well, obviously, if there's a significant, like in this case, it sounds like there's a significant computer cost is just part of the development. It's a lot more than would be with a typical AOGCM.
Yeah.
Then that is a factor because you kind of think in terms of typically what it takes to get an AOGCM to run, and you have some idea that that may be a total of a couple thousand years or probably less. I don't know what the total. Do you know what the total development time was for CCSM3? It's probably less than 1,000 years.
Yeah, probably less, but then in the end, then we did 1,000 year control.
Right, but that was
No, it wasn't less
part of
than
the
1,000 years. Oh, maybe. Well, not on the atmosphere side. I'm sure.
Ours wasn't less than 1,000 years.
Yeah.
We did 300 runs or something.
Construction. 10 years each.
It's also, I remember when you guys were doing that, the other problem was you needed rapid turnaround on the runs and almost dedicated access to the machine, which you guys get automatically, but they had to kind of scrounge around, and they finally found some so they could get the rapid turnaround, because you had to try to get the stuff in overnight and get it back out, because our hack was going crazy.
But the point is, there may be like a factor of 3
Just that most
more development time
This is legitimately
for this carbon cycle stuff.
Is it
I think that's a good point. You should
Jerry,
put that on the-
it's a lot more than 3.
Is it?
Because unlike what we did before, where say GFDI, I think we did order 3,000 years of AOGCM running before we had the model.
And that was
Every
just all
time
your
we
testing
changed-
and development.
That's right. In this case, every time you change the model, you got to go through that. If it's 6,000 years of initialization, you would have to in principle.
You'd only do it, sure, but you
wouldn't.
I don't
do
think you
that.
can do this in coupled mode.
In fact, I doubt if you do it once, let alone a whole bunch of times.
No, I think you'd have to do it ocean only.
Well, driving them, at least in our ocean only, is a problem.
Is it?
Because it doesn't behave very well. We have actually given up doing ocean only.
Yeah, we gave it up also. We gave it up because it didn't seem to have any relevance to what happened when we then coupled it. We changed parameters in the ocean only run, get a certain response, change that same parameter in the coupled model, got a very different response.
That must say that your atmospheric driving isn't that close to the observations you drive.
Or the way you apply the atmospheric driving to the ocean only model is not consistent with
Well, you could.
Which is why
It is in our
I mean, that's why there's no OPNet.
The
Notice
ocean
that
model
people
doesn't-
don't settle on how to drive an ocean only.
Right. Well, one of the biggest problems there is when you try to spin up with an ice model. Where they,
Or not, right.
yeah, where GFDL really got into problems was when they had an ocean of ice spin, and then the North Atlantic overturn disappeared. That's they didn't like that.
There was good reason.
By ice you mean sea ice?
Yes. Yeah, so they tried to initialize the
That ended that line of investigation.
But right. Whereas we actually just spun up the ocean and we didn't have that same problems. And that depends a lot on then in the ocean only, how do you parameter or drive the sea ice, what the sea ice is doing to the ocean.
Yeah.
Because clearly that drives a lot to do with the brine rejection and the overtake.
There was also an issue in our model with the, we couple every 2 hours. And so the wind work that's effectively being passed is different when you do an ocean only. Typically you have winds that are daily or even monthly. So there's a lot less work going into the ocean, so the KPP coefficients are different and so on and so on.
So this is going to be a
potential showstopper.
Yeah, exactly. Let's just not worry about it.
Yeah, right. We won't worry about it. We just do terrestrial.
We all get to solve it, right?
So it sounds like we're going to have to talk about this a lot more tomorrow. So shall we move on? This is going to be a. Oh yeah. So other requirements for the scenarios: nitrogen deposition and ozone concentration near the surface. And then the last one, actually, Peter, you have to help us with because none of us understood. CO2 emissions disaggregated or gridded.
Yeah, that's only for the periods where you're running CO2 as a tracer for validation against advanced emissions.
Okay.
Things like the north-south gradient, which is partly driven by where the emissions are. It's a good test for your model. So that's all.
That's what we sort of
that's all.
use for diagnostic purposes.
Yeah. So it's only
So
that.
the question
period.
is that really a scenario requirement, or is that just a?
It's not part of the scenario requirement. It's the historical
model
emissions.
development.
Yeah, it's historical emissions bit.
So are these element like nitrogen deposition, ozone concentration to the surface, are those typically part of what the scenario community would be able to provide? No.
So that's what the chemists would have.
So atmospheric chemists would have to provide some of that?
Which is what you already do, right?
You've been offering them for ages, we just never used them.
Well, the nitrogen deposition, we have something. Ozone concentration near the surface, we don't. I mean, we may have something for like some time slices.
Yeah, sure.
And I wouldn't know how to do it like 2100 if we haven't done it right already. So, but we could provide that once we know what frequency.
We could do that offline like you
That's
did
right.
the 20th
Time
century.
slices, yeah.
I mean, you just have to have some previous run of an AOGCM with that scenario in it,
That's right. And then you run the model offline with the scenario emissions, so to have some consistency.
Right.
Okay. So that we should move that into a different category, I guess. Not sure where.
Yeah, in some ways that could go in the validation bit, the CO2 emissions.
Yeah.
As well. Yeah.
Both of those. Yeah. And then the last thing is just this is actually just sort of a smorgasbord list of improvements. Linda wanted to stress before she left that better representation of agriculture, particularly the management, having different crop types, phenology as well. So I think that's a relevant point. I don't know where we're at in terms of that.
Well, right now, isn't everything kind of like corn? Or everything?
Yeah, it's grass. Most people that are doing this at all right now are planting grass wherever there's cropland.
We have a crop, but it doesn't have which is corn or wheat or something like that. But it doesn't have. There's not a crop model associated with it, so it doesn't have phenology and there's no irrigation. So it's just the only difference is a few difference in the parameters, which probably doesn't have that big of an impact.
Probably not on a large scale. So it's one of these things that gets more important as we start to resolve.
Yeah. So I'm not sure how important this is. Linda definitely brings this up every time we talk to her. So.
Like management is potentially huge.
Yeah, exactly.
I think she's shown it's important in regional climate models.
Yes, he's definitely. So I mean, phenology in general is important, and whether or not it's crop phenology relative to just natural phenology, I'm not sure how important it is to distinguish those.
Well, the management's huge. I'll give you a good example of that is I think something like 30% of U.S. cropland is now in no-till agriculture. So that has very different consequences for soil carbon than tilling agriculture does. And there's a no-till, so they don't plow every year.
What's an example of that, just for my something?
Well, it's
a crop that you don't plow.
Well, they do it with corn. They do it with.
Oh, so this is just a new way of.
It's the same crop. It's just a different management. Yeah. But some of the new studies that just came out in the past year show that while that sequesters soil carbon, it actually ends up emitting more nitrous oxide. So the radiative balance of doing that is like the sign changes as soon as you include nitrogen in your biogeochemistry.
Wow.
So there's a lot that's going to come out of this management term. I think she's right about that.
But yeah, but then
this is all in that category which we put into the possible. Maybe should be in Vanguard. It's right on the edge whether you're going to be really treating your land management properly or not. Right?
Don't you have to parameterize human behavior then? Because farmers are going to have to decide, based on how the climate's changing, what they do with their crops.
That would have to be part of the scenario somehow.
Okay,
so.
Sure. Strangely, the models will deal with things like the possibility of planting C3 instead of C4, or just having veg dynamics there.
As long as you're talking about C3 versus C4, it reminds me of something I meant to ask earlier on, which is there has been this speculation, at least, that addition of a great deal of aerosols could change the amount of diffuse and direct radiation, and that could in turn affect the balance of crops or vegetation. And I think we did one preliminary calculation in which we looked at this and didn't really see a big effect. But have other people done this, and do they think that this is worth revisiting? Should we be producing products which actually identify the amount of direct and diffuse radiation?
Yes.
Yes.
I think so. We didn't put that on the list, and maybe we should, which is the distinction between diffuse and direct radiation in the photosynthesis models. People are certainly working on that, and in some regions it looks quite big.
Well, with that in mind, for the DGVMs, what degree of complication do you think needs to go in to look at the radiation as it penetrates into the canopies? You know, GIST people are now spending a lot of time on that. Bob Dickinson way back when spent a lot of time on it. What's the current thinking? Do people feel that's an important issue?
In order to do the diffuse direct radiation stuff, you have to go back to the complexity of models that Bob and people developed and go a little beyond that. I mean, the models that we currently have are essentially big leaf type radiation models, and they don't get the diffuse direct radiation. They couldn't care less. So in order to deal with that, you actually have to do the radiation much better. And I think a number of models will do it. Not all.
Radiation inside the canopy.
Yeah, the canopy radiation interception you have to do better. But some models do that, some don't. I think more will by the time of the next assessment.
Yeah, we've made some improvements to our so probably a lot of groups I suspect are working on that.
So perhaps we should.
And made a big difference to the carbon.
Yes.
It made a big difference to the photosynthesis and therefore the carbon cycle. So I don't know if that's actually a point to be made, or is that just going to happen naturally in all the models as they see fit?
You know, it requires a different coupling. You need information from radiation codes you might not necessarily have.
And so then,
I just elaborate on that. The within canopy radiation stuff is actually really important to having your plant functional types coexist within a location. Because the major trade-off in the coarsest plant functional types is shade tolerance versus rapid growth in high light. And so to get those things to coexist, you have to represent places that are shaded at the forest floor versus places that are in full sun at the forest. Or you won't have your plant functional types coexisting in the first place.
yeah.
So that's my version of yes.
Except for we don't do that. So this one is slightly controversial, or basically just how to deal with errors in the AOGCMs, whether we should be considering what we would do. I guess the way I was thinking about it is what we would do if after asking the atmosphere model working group very nicely to get better Amazon precip, then they didn't do it. And then asking nicely, then I know. But that suggests a question to be raised: is that what if there are some, as Ron put, actually the showstoppers? But do we really want to stop the show if you don't have enough precip in the Amazon? And we just brought up the question whether or not, and I think even our group said that they'd definitely prefer not to do this, but to consider whether you should tune your model, vegetation model, or the land model to get a rainforest where you don't have enough precipitation. I think most people said they wouldn't want to do that, but we wanted to raise the issue. If anyone has.
The alternative is no Amazon. I mean, you got to come up with something.
Well, that's the question. If the alternative is no Amazon, what do you do? The other possibility is to just deal with the fact you have no Amazon, and then just.
You've got an Amazon. It's just savanna.
Well, oh yeah, sorry, yeah. No rainforest in the Amazon. You just deal with it, and just have to basically be writing that in your analysis that this model didn't actually have an Amazon, so these results have to be interpreted in the context of there not being an Amazon. I don't know.
But
so,
anything else you do becomes arbitrary.
That's right. That's right. So that's the question: is what's the most defensible thing to do? I guess. And
So
I
how is it different from any other AOGCM area that you have now? I mean, we all write papers about with models that have double IPCZs, and it doesn't seem to bother too many folks.
Well, that depends on who you're talking to.
Phrase it that way, it bothers us, but we don't know how to fix it either.
But it may not be the same. It may not have the same problem, at least in public perception. Not having an Amazon is going to affect people more than Amazon rainforest. Sorry, an Amazon rainforest is going to affect people more than having double IPCZ.
Right.
That's true as well. Yeah.
I mean, this is the flux adjustment, carried back to the early days of Suki having no overturning in the Atlantic. So you have to get the density right in the North Atlantic, and if you had no radial overturning, that was deemed as unacceptable.
Yep.
So this may be the same thing. If you have no Amazon rainforest, that may be unacceptable. So you do something that's not very palatable to get one for now, and until the model gets better.
Sure. I'm optimistic that if you do, as you're suggesting, Dave, when you do this coupling early on, we look at the coupling classification, that there will be a new focus on certain areas in models that will get sorted out.
Yeah, we're almost begging the land group to provide us with these kind of diagnostics.
If you have a small set of things, it can't be
less than 5.
A small set of things, I almost guarantee you that you can make them work.
Yeah.
Because that degrees of freedom,
yeah, I think so.
Yeah, but the thing is, you got to make sure that making them work doesn't hurt something else.
Oh, it absolutely will.
It's not on the list.
That's part of your shit. That's why it's right.
We found, for example, that one of the big issues in modeling is the marine stratus, getting low-level stratosphere. So we found that a lot of things we could do that would improve marine stratus would hurt precipitation over land in the tropics. Yes. So what's your choice? What do you do?
Yeah, well, we've been able to get rid of the double ITCZ really easily. It just screws everything else up.
But Ron, aren't you? You're in this situation right now, right? You can't sustain the Amazon rainforest through existing precipitation regime. So what are you going to do about it?
It's going to be a lousy simulation.
So you're just
the Amazon rainforest.
So you're going to let it die, and that's going to be it.
It's going to be partly rainforest and partly savanna. I think. I mean, you can't tell because the model develops.
Right. So you're not going to do any.
Nothing good in the precipitation, correct?
Nope. If I have anything to say about it.
So.
Definitely not.
I mean, this is the thing that always bothered me. You took the couple modelers took years to get rid of flux correction, and it wasn't until they took that step that there was any credibility in their results that they could make with anybody who was legitimately skeptical of the results. I'm not talking about the people on the extreme. People had legitimate reservations about the model results because of the arbitrary flux adjustments. And then you got this whole new community coming in, going back down the flux correction road. And I don't think you're going to have a credible result as long as you have arbitrary flux correction. You're just not going to be able to persuade anybody that your climate change simulations, you'll be able to persuade some people, but you're not going to get the critical mass of people with legitimate scientific objections to those arbitrary adjustments to buy into your conclusions.
Also, the more you don't put pressure on the atmospheric modelers by using these equivalent flux adjustments, the less incentive it is for the atmospheric modelers to avoid embarrassment and improve their model. You put pressure on them by not doing that and publishing papers showing, look how bad it is.
They're not 5 years old.
A few more years.
Just to Dave's point is correct, but of course I think you also would have to say, would people question the validity of a result when you didn't have an Amazon rainforest, knowing full well that previous model results have shown that it's extremely sensitive? Easily scientifically to understand.
Tell me the credibility you have, though. You do the flux correction, and then you do a climate change simulation and say this is a realistic projection of what's going to happen.
Well, flux correction might be the wrong term.
Which is what they've done, which troubles me, actually.
Flux correction could be the wrong term. Another approach could be to have a local change or a global change to the way your land surface retains water. For example, would be another solution, which we actually don't have a particularly strict validation date on anyway. So you could just say, well, since we aren't getting the Amazon rainforest correct, maybe it's because we aren't retaining our water in the atmosphere.
So we just can turn off the Amazon River or something,
well,
just retain the water.
I haven't thought exactly about how to do it, but I mean, you could change your soil characteristics for one thing. I mean, that would be one way to do it.
Only do so much of that.
I mean, you don't get enough precip. You're not going to be able to. You'd have to also affect the evaporation, evapotranspiration, which would keep.
Yeah, but all these knobs are available in the more sophisticated land surface process models.
Right.
It's relatively easy, I think, to screw with them.
But that's what I'm right. You could
like
you could
you
do
said,
it.
it's not known what these coefficients are for a lot of them.
Yeah.
So it is possible to do it. In fact, I've been arguing with folks at GFDL not to do it.
Not to do it. So, okay. Well, so we agree to not to come to any conclusion. Or I don't know. I think it's obviously one says that much rather not do a correction. Right. But I guess I still wonder if we should be at the same time having some sort of a discussion about, just to make sure that we're comfortable with. If the Amazon precept doesn't get corrected, that we're comfortable with that. If that's the way it is, then that's fine. Right.
I mean, there's also an argument about whether the right thing to do is to have flux corrections or to tune your model to make sure you don't need them, whether you change the sensitivity, and there's the same argument with the vegetation. Right. It's not necessarily better to tune the model with so it's got ludicrously deep roots than it is to have some kind of flux correction.
Right.
but I'd rather not. I think if we throw it into their core early on, it'll get salted.
Okay. Well, that's what I think most. It sounds like most groups are trying to do. I mean, you're gonna get something within days, I imagine. And we sort of talked about showstoppers and metrics. So, and then just basically considering other ways to improve the carbon cycle. Correct me, is this the right way of saying what you were trying to say through method of other observations, so other modeling activities? The ocean, in terms of the ocean, the flux of CO2 at the interface, I think Mishri was saying that eddy parameterizations are not always adequate to reasonably simulate the flux at the interface? Or is that a potential improvement?
What I said is eddy mixing is definitely necessary for
Is necessary.
Yeah, for representation of the ocean's uptake of CO2. While some of the, I think some of the SIFOMIP models lack it.
Okay. So possibly that
the biogeochemistry traces are quite dependent on eddy resolution. I mean, ocean model resolution.
Okay.
When if you're resolving the eddies, things happen with sort of on-off switches, which we don't get with non-eddy resolving. It's not absolutely clear that mixed parameterizations do that.
Is that going to be part of the core of the eddy resolving ocean models?
Yeah, once you get the eddy, if you get eddy resolving, then you have enough resolution.
Well, we're not going to have eddy resolving.
But sometimes you need eddy parameterization. That's our experience. To represent enough activity of eddies in some
You parameterize that.
Yeah, using the same parameterization used in the coarse resolution models. That's what we experience using the eddy. Eddy permitting.
So most models will do that, sort of parameterize.
I don't know, but
from eddies.
So even if you quote resolve the eddy, you still have to have closure for the scales that are below the eddies. We've shown that if you do them the same way, you still get nice results with respect to those pixels below the mixed one. We've also done something where we've improved the transition between the deep ocean eddy mixing, which then goes along isopycnals, to what happens in the mix layer. And we've got some fairly nice results, and those will help and improve when you have pure traces.
So I guess that the real message, which is true for all aspects of the model, is that the physical models need to be developed in concert with the biogeochemistry, at least having it in mind as a
right.
That's probably obvious, right?
Is it because without eddies, is it possible to do the ocean biogeochemistry approximately correctly? I mean, isn't that a key? You can
it is, of course, but it depends what you mean with the word approximately.
Yeah, okay.
It's the ocean.
Within the gigaton per year.
Then it's okay.
But your point, Peter's point, was just as the parameterization, as the physical climate models improve, then the other part, the other component, their simulations will hopefully also improve.
Right.
How about adding CO2 inversion technique to factor bullet?
That's part of transform.
Okay.
And then just the last thing is to probably want to have in this document a plug for observations, because this is, I guess you take every opportunity. And so George mentioned is basically almost any observation in the southern hemisphere. There's just not enough observations in the southern hemisphere. We talked about a few things. Carbon stocks, land use management patterns, for example, are just a lot not as well known in the southern hemisphere as they are in the northern hemisphere. Soil moisture, of course, I think is an obvious one and a timely one with the recent, I think, cancellation of the satellite mission. It's pretty important in the carbon water cycles to know soil moisture, and then satellite measurements of vegetation structure. Does anyone have any additional pressing needs in terms of
Well,
observations?
those Argo floats are also global.
Right.
They're everywhere, and with the new Clivar repeat hydrography transects, that will improve some of our detailed observations in southern oceans and other ocean basins.
Right.
That's
Yeah, so the Argo floats could be exploited to perhaps.
How about I mean, this is the wrong time frame, but a remote sensing of colorimetric CO2?
Well, there'll be OCO is scheduled to launch late 08.
Right.
So that it probably won't launch until 09, and if we might be able to invoke some of them but I don't know that anything will be really available in time for AR5.
Not AR5, it'll have to be beyond, yeah. Okay, it's probably worth flagging up though. This is potential.